Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Jr., the math tutor, and in my today's lecture, I will be looking at differential equations. So under differential equations, particularly, I'll be looking at the separation of variables or variable separable. So we said in our last or in our previous videos that whenever you have a differential equation and you are capable of separating the terms in x from the terms in y, thereby putting the terms in x on probably the left or the right, and the terms in y probably on the left or the right as well, but separating them, putting one on one side of the equation and the other on the other side of the equation, then it means that you can apply variable separable method to solve the differential equation, thereby finding the general solution. If that is not possible, then it means you must apply other methods. Like we have the reducible to variable separable, we have homogeneous differential equations, we have exact differential equations, we have integrating factor, and a lot of other methods that you can use on the first order differential equation. So yeah, let's get started. Thank you. So in question number 4, we have similar problem. So in this question, we want to solve this problem. Yeah, but the difference between this problem and the previous problem was that we had x right here, and then I had y here. Now I replace this x with y, and I replace this y with x, so that we solve the general, we find the general solution. So let's go. Again, we want to separate the variables. So since we know that y is the name of the function, so we always want to have like y on the left hand side of the equation, right? So that it makes some sense, though it can appear any side of the equation. So we have secant square x tangent of y dy, and then this side now we send this term across, it becomes negative secant square y tangent of x dx is equal to 0. So we need all y here. So this is already y. So we can divide this side by secant square x. We divide this side by secant square x. So we also need, on this side, we need only x. So this secant square y, we divide on both sides, secant square y. So what happens? This and this will go out. This and this will also go out. You have tangent of y dy is just equal to negative tangent of x dx all over secant square x. Now, we know that the derivative of secant is equals to secant x tangent x. And if we say let u be secant of y, if we differentiate secant of y, we are not going to get tangent, that's a secant of y, tangent of y. Because in the numerator, we only have tangent of y. So one way we could do it, since we have now separated the variable, so we are integrating now. So one way we could do it is to rewrite in terms of sine and cosine. So we have the integral of this one is sine of y all over cos of y divide. This one is 1 all over cos square y dy equals negative. This tangent is sine of y, sine of x all over cos of x, all divided by 1 over cos square x dx. So we can rewrite it as the integral of now sine of y all over cos of y times, then we reciprocate this fraction down here, thereby saying cos of y square all over 1, reciprocate. So this one we cancel 1 cos of y from here, just be left with 1 cos of y minus the integral of, so the same thing, sine of x over cos of x times, we reciprocate, so it's cos square x all over 1 dx. So we can take 1 from here as well. So we left with cos of x. Great. So therefore, we have the integral of sine of y cos of y dy equals negative the integral of sine of x cos of x dx. Great. So we can bring in some identity. Or if we can just say, let u be sine of y. If we differentiate sine of y, we get cos of y. We could say, let u be sine of x. We differentiate sine of x, we get cos of x. So it makes no difference. Or we could also say, we know that sine of 2x or 2y now is equals to 2 sine of x cos of y, or cos of. So we're using y now, so the variable should only be y. So we know that this is equal to this one. But we only need sine of y cos of y, so we can divide this out by 2 and as well divide this out by 2. So this 2 and this 2 will go out. So it means sine of x cos of y is just equal to this expression. Great. Great. But so we just use, we say let u equals sine of y. So the u now is equals to what? Cos of y dy. On this side, we say let v equals to sine of x. So the derivative of v now, which is the v, equals to what? The derivative of sine is just cos of x dx. So this one now is just equals to what? This is equal to the v, and then this is equals to v. So we have the integral of sine of y, which is now u, times cos of y dy is just du, right? Equals minus the integral of sine of x is just v, times cos of x dx is dv. So we integrate. We have u squared all over 2 equals v squared all over 2 plus some arbitrary constant c. So what is u? U is sine of y, so it's sine square y all over 2 equals minus v square y, or let's say v squared now is just equal to sine square x all over 2. And then we have plus arbitrary constant c. So we bring it up here. So now we have sine square y, right, over 2 plus, because we're sending that one across, sine square x all over 2 equal to arbitrary constant c. So we can multiply all sides by 2. So 2 times this, you will just be left with sine square y. And then 2 times this, you'll also be left with, you'll be left with sine square x, all equals to 2c. So you can stop here, or you can say sine square y plus sine square x, all equals to what? To just arbitrary constant c, instead of saying 2c or 3c or so forth. Just c. So this is how we find the general solution using variable separable for question number 5. Very, very easy. Thanks for watching. Please subscribe and see you in our next lecture.